Welcome to this lesson from Transparent Physics. This time we are going to be talking about Kepler's three laws. Now, Kepler's three laws is a continuation to some extent of our last video where we discussed the historical development of theories about the solar system. When we left off, Kepler was wrestling with the data, trying to figure out a theory that matched his own ideas with the facts on the ground from Brahe's data. And Kepler was looking at that to try to validate his affection for the Copernican model, which had the sun at the center of the solar system, but also incorporated perfectly circular orbits and planets that moved with constant speeds. And what we find is that when Kepler studied the data, he could not get the data to fit that theory. And ultimately, he had to abandon ideas of the Copernican theory to follow the data in the direction where it was leading him. And he released these in sort of two phases. And what we call Kepler's three laws, not necessarily, I don't know if Kepler himself would have stated his three laws as such. They have been gleaned from his work, and we summarize what we consider to be the important parts. There's lots of stuff that Kepler published that was just flat out wrong. But this work, in terms of his three laws of planetary motion, has withstood the test of time quite handily. So, after lots and lots of research, if you remember from the story, Kepler got the data from Brahe when Brahe died in 1601. I read somewhere in doing research on this that Kepler was actually ready with his book, Astronomia Nova, meaning New Astronomy. His book was published in 1609. As I understand, his book was ready a couple years earlier, but there were some legal disputes with Brahe's family about the ownership of the data, which I guess was ultimately resolved because he did end up publishing his book in 1609. So the first two laws in that book was, first of all, the law of ellipses. When Kepler studied the data, he realized that he could not get it to work for circles. But he was a huge fan of geometrical shapes. He loved geometrical shapes. He was all about them. And he discovered the ellipse worked very well. And the ellipse is a geometrical object. If you've ever done it in maybe math class, if you take two fixed points and you have a loop of string and you keep your fingers fixed and then you take a pen and trace out a circle, the shape that's traced out is what's known as an ellipse. And an ellipse is defined by if you take a line from this point and a line from this point to any point on the outer sort of circumference of this shape, A and B are going to add up to a constant. So A and B are constant here, A and B are constant here, A and B are constant here. And that traces out this shape called the ellipse. Now, this was an abstract geometrical shape known to the ancient Greeks. And what I think is pretty cool about this, now again, first of all, our solar system isn't terribly elliptical. A lot of our orbits are pretty close to being circular. So it's kudos to Kepler for noticing some subtle differences in the data that led him to realize that a perfect circle could not account for this accurately. Also, on top of that, these 2 points here are what we call focal points. These are used to define the rest of the shape. And Kepler realized that the sun is actually positioned at one of these focal points. Now, this, again, is a very extreme ellipse for our solar system. As you move these 2 points closer together, this object becomes more and more and more circular. And a perfect circle is really just an ellipse where the two focal points are sitting on top of each other. So for the orbits in our system, generally speaking, they're not super elliptical. So these focal points are much closer to each other. But the sun sits at one of the focal points. The other focal point is just empty space. So that's pretty awesome. And again, not easy to do. And if Kepler had stopped there, I don't know if I'd be doing a whole video on the guy or not, but definitely I think his name probably would be remembered for discovering that relationship. But in his book, he had two relationships at the same time. The first one, again, the law of ellipses. The second one is the law of equal areas. And this, if the law of ellipses knocked down the idea that all planets traveled in perfect circles, the law of equal areas knocked down the idea that all planets move at a constant speed. And again, remember, Kepler was all about geometry and shapes, and he was able to do this again. And what he realized is, as he was studying the motion of the planets in Kepler's data, he could imagine a line connecting the sun to the planet. And again, this is very elliptical, and I wouldn't consider any planet in our solar system has an orbit this elliptical. But for the sake of the diagram, let's imagine the planet's spinning around like this. And what he said is if we imagine that these two wedges represent the same amount of time, that if this right here is 2 months and this right here is 2 months, that a line, if the planet starts here and we go 1 month and 2 months, and then the line starts here and we go 1 month and 2 months, this amount of time and this amount of time is the same amount of time. And if you were to calculate the area swept out by a line that connects the planet to the star, this shaded area and this shaded area would end up being the same. So what he noted is the line connecting the planet to the sun sweeps out equal areas in equal times. Now that is true from a geometrical standpoint, and again, Kepler was all about that. From your perspective as a introductory physics student, what's more important is the corollary that what this means is if these represent the same amount of time, that when we are looking at this, if this is 2 months and this is 2 months, and I just arbitrarily made those up, that you can see that the distance the planet covers in these 2 months is much larger than the distance that the planet covers in these 2 months. And what it basically meant is as the planet gets closer to the sun, it speeds up, and as the planet gets further away, it slows down. You know, for example, like Halley's Comet is an extreme example of an object with a pretty elliptical orbit. So that Halley's Comet will come through the system, buzz through at a pretty high speed, just hang around for a couple years, and then fling itself back out to the outer reaches of the solar system and disappear for, I don't know what it is, 76 years or something like that. So it spends a lot of time out here moving relatively slowly, and then it comes in and flings itself around real fast and then goes out again. So these two laws were published in 1609, and it was awesome. You know, these are the exact kind of things that Kepler was hoping to find out. They are geometry based. They're showing him the patterns in the heavens, but he felt that there was more, and he continued to do his analysis. But now's a good time to maybe stop for a sip of tea. All right. And that sip of tea takes about 10 years. So, because Kepler's next comment on this particular topic happens in 1619. And he publishes an additional book called Harmonies Mundi. I don't quote me on the pronunciation, but it means harmony of the world. And again, this was all about Kepler's attempts to connect the data to his theories on sort of the musical, compositional origin of the universe, that there's this like order in how the universe was designed by God that can be represented in these geometrical shapes, and you know there's like a hidden pattern in all the data. And the book goes on. I think it goes. I think I read somewhere it's quite a few volumes and stuff. Basically, in the last section, he brings up what we know now as his third law, and it's we call it the law of harmonies. And the law of harmonies is easily the most mathematically rigorous of the three. But as an introductory physics student, it's going to be the one where you're actually going to be taken. Where the rubber hits the road, and you're going to have to actually do some calculations with it. It's not a pretty equation to work with, but it is admittedly very elegant. I'm pretty impressed with this. So if we take a look at the equation itself. Word-wise, it's a bit of a mouthful. Kepler recognized that the square of the orbital period of the planet is directly proportional to the cube of the semi-major axis, aka the average distance of the sun, of its orbit. So he noticed that there was a relationship, long story short, in how far the planet was from the sun on average and how long it took to orbit. That it wasn't just coincidental, that there was a pattern there. For our intents and purposes, when you work with Kepler's third law, you will probably be using this version of the equation. And A and B are two objects orbiting the large central mass, maybe two planets orbiting a star. So if you take T, capital T stands for orbital period. If you take the orbital period of the first planet, which is how long it takes to orbit the sun, and you take the orbital period of the second planet, divide one by the other and square it. Then take the average distance from the sun of the first planet and the average distance from the sun of the second planet, divide those by each other and cube it. The square of the ratio of the periods is going to equal the cube of the ratio of the distances. How he figured that out, again, he was working on pre-computer time and stuff like that. It's pretty darn impressive. When you take a look at that data, well, and again, when you calculate it, I'm sure we'll have a video showing us how we can go about solving Kepler's third law. But when you're working with it, because these are ratios, it really doesn't matter what units you choose. So this is one of those rare instances where you can not necessarily worry about the metric system. If you have years and years, that's fine. If you have weeks and weeks, that's fine. You can do anything you want to. Distances, miles, kilometers, inches, light years, whatever you want to do, as long as it's the same on the top and the bottom, we're just looking at the ratio between the two distances. So keep them consistent, and you're good to go. Bob's your uncle, as we say. A interesting effect of this relationship is that, it's saying there's a relationship between the squares of the periods and the cubes of the distances. If you take, say, for our solar system, and you plot the data, and if you take the orbital period of each of the planets, and you square that number, and you take the average orbital radii of each of the planets, and you cube that number, and you plot those dots, you're going to get a pretty sweet linear relationship when it's all said and done. At least, once you square and cube it, you have to fiddle with the data to get this to work out that way. And this is consistent. If you take a look at, say, planets around, if you take a look around moons around Jupiter, and you plot the orbital period of the moons and the distance of the moons from Jupiter, you're going to get this relationship. Again, this relationship is not just for our solar system. We can look at it for objects orbiting central masses. We can even apply this on a galactic scale, like our Milky Way galaxy. We can actually study our stars orbiting around the galactic center of the Milky Way galaxy, and it scales up and down quite elegantly. Now, take these three things together, the first law, second law, third law, and it is a remarkable accomplishment. Not even getting into the fact that Kepler himself had a pretty rough life. He was all pretty much often on the move, and wasn't necessarily very well off financially. Had personal problems and health problems and all kinds of stuff. But through it all, he kept to his faith that there was a pattern that he was meant to find, and he had to give up the kind of things that he really bought into to begin with. The idea that he couldn't get circular orbits to work out, so he had to abandon it. He couldn't get uniform speed to work out, and he had to abandon it. Uniform speed, this was one of the reasons why people hated the Ptolemaic system to begin with. If you remember, Ptolemy said, hey, by the way, I don't think these things all move with the same speed, so we're going to add these equants in here. But it works out really good when we do it. And Copernicus, in revising a system, hated the idea that the speed didn't stay constant. And Kepler was a big fan of the Copernican system. So to give up this uniform speed, it was no small potatoes. But he let the data tell him where he needed to go. He had his own ideas about what he wanted to see, but he recognized when the data was telling him something different. And so I thought this was a neat quote from when he published the results of his work on the third law. I think he wrote the entire book in Latin, by the way, so this is a translation. But in the end, taking up the endeavor again on May 15th, this picks up with the idea that he had originally considered these ideas for the third law earlier, but he abandoned them because he thought he had screwed up. So he had already actually been on the right track a couple months earlier, but didn't recognize it at the time. So this is what he's saying here. In the end, taking up the endeavor again on May 15th, light overcame darkness in my mind. The convergence between the observations of Tycho Brahe and my own elucidations were such that at the beginning, I thought I had been dreaming. So he found this pattern that he was so hoping that he would, and when he found it, he didn't even think necessarily he could believe what he had found. But again, a lot of hard work paid off, and so now he gets some random physics teacher talking about him on YouTube. So what better accolades could you hope for? Well, there we are. That's Kepler's three laws. We will turn back to them again when we start looking at the math of the third law. That does require some extra skills, but concept-wise, I think you guys will have everything you need right now. So I hope that this lecture has made things a little clearer for you. And thanks for tuning in to Transparent Physics.